Yeah. So very warm good morning and heartily welcome to all respected faculty members, researchers, practitioners and industry persons who are attending this 5 days FDP on quantum artificial intelligence. So it is an honor and great pleasure to welcome you all again on this last day of FDP on behalf of Department of Computer Science and Engineering, IIIT Pune, uh, and organizers of this FDP. I welcome you all. We are at the 13th session of this FDP, day 5, session 1. So today, for this session, we have with us Mr. Srinjoy Ganguly, founder and CEO of AdroitERA. As we all know, sir, as we had wonderful sessions, uh, hands-on sessions rather, by sir on the third day of this FDP. So in today's session, along with sir, we have one more guest speaker with us, Miss Gopika Chaganti. So in today's session, madam will start with the introduction to variational circuits and its relation to classical machine learning algorithms. So we will have a brief introduction to the concept of quantum gradients using the parameter shift rule and its significance with implementation using PennyLane. We will see the implementation of variational quantum classifier, which is equivalent to quantum neural networks using PennyLane. So I take this opportunity to welcome Madam Miss Gopika Chaganti and Mr. Srinjoy Ganguly sir to join with us for this session. So thank you all. And now I would request Gopika ma'am to please proceed with the session. Thank you. Madam, you are not audible. Please unmute yourself.
Yes.
Yeah.
So sorry about that. This always happens. Yeah.
Okay.
Thank you so much. I should again go back and thank everyone. So thank you so much, Mr. Darshan, for the kind introduction. My name is Gopika. A little bit about me is I am currently as an IBM quantum educator, and I'm also working as a trainer for quantum computing. Yes, I think that's a little bit about me. Before that, I've worked for over 6 years in academia, and currently I'm also a project manager in a startup for Canadian market. A lot of things, beautiful things are happening. So I just fell in love how quantum is working with the classical conjectures. So we're not there yet, but we are very hopeful as of now. So also I would like to thank Mr. Ganguly for this opportunity. It's always good to interact with the academia. So yeah, should I present my screen now?
Yes, ma'am, please.
Thank you. So there is a bad network, so I might go off and on with my video. Please don't mind on that.
Okay, please.
Yes, you should be able to see.
Yes, ma'am.
I'm sorry for the first line. Yeah. Okay. Okay. This is the session 4. I'll give you a brief introduction about why we are doing this. Okay. So it's always good to have a motivation to start with. So what are the applications? So I'm not talking about the application of variational circuit. That is one way we are actually implementing quantum machine learning in this hybrid classical quantum intersection. But what are the applications of these algorithms or this technology as such? So I'll just give you a brief explanation about these 4 categories of applications. So when we start with logistics, so we do know that logistics involves a lot of variables, a lot of combinations. So it comes under a problem of combinatorial optimization problem, which comes under again an NP-hard problem in classical computing. So there is a higher chance of these quantum algorithms with the help of classical, if we get there in this era, otherwise by themselves, give good results in logistics. an example can be transportation, and you want to transport your goods to various places, and you want to have the optimal paths, optimal routings by, working on various variables. We all know traveling salesman problems, so I think I don't have to get there. So that is one kind of thing we are looking at this part. So yes, finance. We are interested in finance, aren't we? So is there a good way that we can actually assess our risk when we invest on a stock in a company? Can we assess that risk? So this actually takes a lot of data, a lot of historic data. We call it big data in classical computing. We didn't have a term here as yet. But in finance management and modeling and risk assessment and portfolio management, can we have good algorithms which actually propose optimal results? So I do remember there was a participant, there was a faculty lady who was interested in this domain. So what I would suggest is please closely follow what Goldman Sachs is doing. It's doing wonderful things. Recently, it also had a breakthrough in actually working on this partial derivatives of various stocks. So I think I propose to follow Goldman Sachs. They have a research division for especially quantum computing and machine learning. Yes, material sciences. Obviously, this will have a higher experimental result which we can see in a near-term future. So when I talk about material science, I'm referring to the drug discovery, working closely with the molecules, which is quite hard in classical interface, because to bring a molecule to its ground state energy, and then calculate its variables is quite something not so easy in classical setting, which again, quantum would theoretically is making to seem possible as of now. And recently there was this DeepMind company which has a protein folding problem. It has solved it. So there is a conjecture that what if you solve the same problem using quantum? And also this is there. What if we already had quantum computing now? The COVID drug discovery would have been a lot earlier. So there is also that part. So this is basically about the chemistry aspect of it. So yes, the universe, right? So when we talk about quantum, before we know anything about what quantum is and everything, we know that there is a lot of Big Bang theory happening. There is a black hole. There is a lot of experiments. What is happening in the outer universe? So I'd like to quote. Maybe I'm just paraphrasing. Apologize on that, but on Richard Feynman, he said that if you want to model universe, if you want to understand how nature works, basically, your system should be something dealing with in the quantum sense, not in classical sense, because nature, by nature again, so is quantum. So if you want to do that, you better have some systems which are quantum, which can actually simulate the quantum system. So when I say quantum system, I'm referring to nature. When I say quantum system, I'm referring to quantum computing system, a physical system. So yes, so these are the 4 major applications. Yes, okay. Sorry if I took a lot of time on that. Quantum machine learning. So yes, we're talking about this. We know this part, the later part of machine learning, we have been hearing a lot since a long time, but since 5-6 years with the advent of GPUs and TPUs and Nevada, Google, everybody is like all over the place with machine learning, and we are into deep learning today. But what quantum machine learning basically does is it falls in this red category. Before I explain what this red category is, I would, if you ask anyone what quantum machine learning is, they would basically say it falls in one of these 4 categories. This CC being the typical classical machine learning. So the first column basically refers to your state of data. You might have a classical data which is working on a classical system. You might have a quantum data which is working on classical system. You might have a classical data working on quantum system. You might have a quantum data which is working on quantum system. So when I mean classical data, classical system, it is something we all do day in and day out as machine learning engineers, researchers, or anyone who is interested in this. This is what we do on our systems, laptops, desktops, even mobiles today, thanks to the technology. So what is quantum data and a classical system? For example, I would like to give here, quantum data is nothing but what if we have data which is simulating the universe. So it is quantum in the sense. We would like to actually model the data using a classical system. We can consider it as a neural network on our classical system. So this is one way of doing it. So we are not yet here, having a quantum data on a quantum system. We are not yet here. There are proposals for this. This is something we're already doing. And classical, I'm sorry, you're able to see my mouse, right? I mean, when I point out at a particular place.
Yes, Manu.
Yeah. Thank you. Okay. So we are actually in this space wherein we have a set of classical data. We want to use this classical data in a quantum environment. Okay, so this is where quantum machine learning falls into picture. So why am I talking about quantum machine learning when the topic is variational circuits? You might get that. So I'll get to that part. But given this very, very brief introduction, we'll be able to relate. So the agenda here is we'll be given an introduction to variational circuits, a simple model, how to optimize a circuit, build it with the PennyLane. This is an assumption which, because Mr. Ganguly was telling you already previously had few sessions on quantum computing, and with his beautiful mathematical hands-on explanation, you might had an overview of how this works. So we assume this, and Nelson and Cheng is the Wikipedia, the Bible of quantum computing information. If you want to, this is available PDF online. So first 3 chapters, basically, if you're good, well-versed with first 3 chapters, you're good to go with variation circuits. Yes, so yeah. Okay, machine learning 101, moving on to variational circuits. This is something we all know, we all have seen, and we are trying to model, we are getting these categories. So we have a data set of, say, X. We have a set of data, which is X. We want to find a function. We want to actually model this data to get a result, get a category, get a class, get a prediction. What we want to do, we will do. But how do we get there? Using set of parameters, right? If you can take in the linear regression or a neural network sense, you have a set of neurons. What do you ideally do is you introduce these nonlinearity, you introduce these weights, the biases, and then by tweaking them, you actually make your model better and better with every iteration, with every training step. That is what this is basically about. This is machine learning 101. So our end goal is to have a model using a set of data and set of parameters to an optimal prediction. That is the end goal. Yeah. Quantum models. Quantum models basically broadly fall into 2 categories. Okay, you have a deterministic quantum model. You have a variational quantum model here, which we talk about variational circuits. Deterministic quantum model is one of the implementation of this is in Darjou's algorithm. Say you have a quantum state on a computation basis. You have a set of operations. When I say you, I mean unitary set of matrices operations, which you know already of. This is the output which you're getting out of this particular circuit, out of this particular model. So what kind of output we're talking about here is deterministic in nature. So you don't have to, take the probabilities. You don't have to come to a conclusion. This might be this, this may be this. No, there is no might and may. It is a straightforward, will this fall into this category? Is this particular function in, the basis of this is in 0 or 1? It is clear and straightforward. It is deterministic in nature. If you want to see the other aspect of it, which we are widely using and which we have all the applications we spoke about, these are variational quantum models which suit the current NISQ era. So it is noisy intermediate scale quantum. So whatever we are having today is something which falls under this variational circuits. This is kind of modeling we do. So what is the difference between the prior circuit or prior computation and this computation is that you observe something called as theta here, on which we are performing these operations, a set of matrices, a set of operations. And we get an output, which is it is in this shift notation. So what it is actually, it is nothing but an expectation value. It is a cost. We are getting a prediction out of this. What do we do with this on this theta is something we will see in these variational circuits. Okay. So what are the prominent algorithms or prominent implementations of these models are variational quantum eigensolvers, classifiers, support vector machines, and neural networks. That you can, we can see these. We know what a classifier is, we know what an SVM is, we know what a neural network is. So what is this in the sense of quantum? I think Mr. Ganguly will be dealing with VQC and QSVM for multi-class labeling. This you can see. Okay, so these, if you want to implement a variational circuit, which we are going to look at today, these are already implementing the variational circuit. So if you know what a variational circuit is, how it performs, you can go back and implement these models in quantum sense. Yes.
Ma'am, sorry.
Yeah.
On previous slide, actually.
Sorry?
Yeah, on the previous slide, I have doubt. Yeah, on this, yeah, right. So in first model, you mentioned that it is giving some deterministic solutions, right?
Right, right.
So means maybe I have taken a wrong concept. So means like how different then it is with the classical computer, because in quantum, I mean, in classical we have deterministic 0 or 1 or like we know, but in
Right.
this, yeah. So
Right. That was a question. Thank you for asking. So basically, what we get out of this can be actually verified. You know, deterministic sense. When we say deterministic sense, we mean that whatever output is there, we can verify it. What is non-verifiable is non-deterministic in the sense. Okay. So
Okay.
to verify the determinism of this particular circuit, this algorithm is actually proposing it. Suppose you work with oracles, right? So when you say that whatever goes into it comes out of, it's a black box. You don't know what is happening in it. Okay, to verify those kind of things, these algorithm, Dutch-Joseph algorithm, Simon's algorithm, actually come into picture in this particular aspect of it. So it's verifiable. Here, you can't say I'm verifying it. You're just taking the sampling out of it. That is this sense of variationalism.
Got it. Yeah. So it means you're talking about that theory of computation, right? Deterministic, not
Right.
deterministic. Okay.
Yes,
Yeah. Got it.
that's a vast subject. Yes,
Yeah.
I'm talking about the basis of that subject here. So basically, when you talk about this part of it, you cannot say it is verified, but you're taking a sampling, your probability of it, and your the term variation. I'm sorry, I didn't explain the term variation. Variational is you keep changing it, so you keep varying it. It's kind of training your circuit. So it's not like this is there and this is the end of it. Okay, so that is
Okay.
so, okay, so this is the quantum machine learning. Okay, you might wonder why are we dealing with the circuits? Why am I showing these lines, these circles, and all? Because we are not there yet. Classically, we have everything performed on the RAMs, which are sitting in this micro level, but we're not there yet. So we need to do the measurements and using gate circuits. So that is the reason we are showing these circuits and all. Yeah, in the sense. So we have set of states. We have set of operations which are performed on a data set X using some parameters theta. Okay. So what we get out of this, if you want to know what we're getting out of this, is something. Okay, you know this notation, right? It's a Dirac notation. Okay. So in a quantum sense. So initially I have shown you what f of x theta is. That is the sense of what ML is. When I just put this Dirac notation, it becomes a quantum sense. Yes, that's the matrix representation of it. So you want to model the function f using the set of data sets and parameters. This is the measurement aspect of it. This is the circuit. I'm building the circuit one by one. Okay. This is the measurement aspect. You need to measure the result. So why don't we measure it in classical, and why do we measure it in quantum? We already know that it's probabilistic in nature. Things collapse, position, everything comes into picture. We need to measure everything. So what we get out of this is a outcome. We are getting an outcome which we will post process, because it is a variational circuit. We need to again train and tweak everything. This is what a outcome is. Okay, what is an outcome here? Suppose you are training using set of labels, set of data sets with cats and dogs. You already have a label with. You will know in variational quantum classifier. You already know a label with you. Class 1, class 0. Class 1 comes under dogs, class 0 comes under cats, something like that. So you basically are getting some kind of prediction here, which you want to train and tweak further. If you see that it's not performing well on unseen data, you would want to again do that. Yeah, I think we have finally arrived here, variational circuits. What is PQC again? So parameterized quantum circuits. So variational circuits are also called as parameterized quantum circuits. We have seen what parameters are. We know what a quantum circuit is. It's also called as. So success of variational models. Why are these variational models? So whatever model I have explained to you in variational sense, why are they successful? Because they are running on near-term quantum hardware. What is this near-term quantum hardware? The hardware which is available to us today in this era, NISQ era. example, IBM is having a hardware. So we don't have that hardware sitting right in front of our, under our systems or at the processor level. We don't have that, but we do have it in the cloud, thanks to, again, cloud computing technology. So whatever hardware which is available today, these variational models are able to run on them. So that itself is quite an achievement. So they're robust to noise. So when I talk about noise, I'm talking about the decoherence aspect of the qubits, okay? Shows most promising in chemistry application. As I told you, the various applications, the third application is the chemistry, which I think most of quantum computing experts, scientists are working on. So this kind of methodology of variational modeling is working on this kind of an application. Everything today is an application specific, okay, that I'll come to that part, but this is working in this domain. Can be used in many quantum machine learning models as well, which I think that is what we want. So this is the success rate of it. Okay, sorry about the pixel of this. So variational parameters quantum circuits, they're basically algorithms with free parameters. Why do we say free parameters? Because as a machine learning engineer or researcher, we have the choice to actually choose, tweak, and train. So we have a set of parameters. We would want to minimize, maximize, whatever we want to do based on a function. We'll come to that function later. So what are the basic steps involved in constructing a variational circuit, which we're going to see in the demo is, we have a set of gate parameters. We are going to train the circuit using it. We will get an output, as I showed you in the before slide. Why do we calculate the cost? Because we want to know whether the result which we have arrived at is optimal or not for the application, for the data, again, in all those sense. As a trainer, as a programmer, only we will be able to assess that. And you need to update those parameters. Why do we need to update it? Because you have arrived at a result. So is the result optimum? It is not optimum. So next thing what you need to do is you need to change something. If you're talking about your network sense, you need to change those weights and then do the same process. Typically, I'm comparing it with the classical sense for now because that is where our understanding is as of in this point in time. So that is the reason I am comparing it. So this is a normal thing. I think everybody knows this. Measurement part, we know we need to measure an observable at the output. So initially I said why, now I'm just using this notation, nothing about it. These are the first three steps. Near-term possible problems. Okay, expectation value. So expectation value again is, how do you do that? You calculate a cost function and then you update it. So basically, we're just talking about this particular circuit here. These are different steps. I think when I give the demo, it will be much clearer. So I've been using this particular notation a lot. So we have nef on x and theta. How we are actually performing this in quantum senses. We are sandwiching our initial qubit, whatever computational basis we have, initial qubit, the final state, in between a cost function. In between a cost function, you can, because we are measuring it in z basis, always a sigma z. You can take that. So in between a cost function, we are actually measuring the initial state and the final state, and then we will come to a conclusion of an expectation value. That is what we're doing. This is something which I have borrowed from PennyLane. So they have these fun circuit diagrams just to not scare us. Yeah. So you have two initial states, two qubits of initial states. You give it, you get a set of, you perform a set of operations on theta, you get a measurement, you get an expectation value, you again send back. Okay, this is the basic building circuit. These are the applications of variational circuits. I don't want to explain them, but you can just see this. Yeah.
I'm sorry. Actually, I lost on that point where you mentioned that we feed the parameters on the previous slide. Actually,
which here one? This one?
The previous one. The second means if it's before of that. This.
Okay, this one.
Yeah. So on this, what exactly parameters are we giving? Means I'm not sure. Yeah.
Right. Yes. Right. So if we have worked on neural network sense, how do we actually use the weights at every neural layer? We will be computing the weights, right? I'm talking about biases weights in the parameter.
Yeah.
Yes. Yeah. I'm talking about them. Yeah. It's application specific because we're talking about machine learning. We are not going to deep learning multiple layers, but we're going to come to a simple circuit. Yes, a simple example. Now I think this will be clear.
You mentioned gate parameters. That's why I'm asking. Like, what is mean exactly gate parameter?
No, because we are modeling it in the gate circuit. So that is the notation I've used in quantum sense of a classical parameters. Got my point?
Okay.
Yeah, quantum sense in a classical parameter. Because when we talk about classical computing, we don't talk about gates, right? When we talk about gates, that is a weird thing because, yeah, in quantum sense, yes. So we have a simple example. We have one qubit. Okay, I'm just taking one qubit. You know, in the representation of one qubit, it can be done in matrix 1, 0. If you want to represent it in a block sphere, we already know it. It just stands on Z. It's a standing vector. It's on Z axis. Spin up, spin down. There are two things here. I'm not changing anything. If you just observe, I'm not changing my initial data. I have a one qubit of which is in state 0. Okay. I'm just measuring it. This is the notation to measure. I'm just measuring it. Okay. Yes, and I am measuring it in sigma Z. I will get something, right? If I measure something, I will get something. It was initially in state 0. When I measure it, what will I get? This is the initial state. This is the final state. I'm getting an expectation value. What is expectation value is my state changed or not changed? So ideally, in this case, it will not change. Yeah. Okay. How do we know that? Because it is 1. My expectation value is 1. We know that it is not changed. It is still in this lying on the z-axis, right? Now, okay. Now I'm just trying to do an operation. I'm trying to do an operation. What kind of an operation? I'm just using this X matrix, which is, it just flips the state of the initial qubit. So when I do that, what happens? If you observe, what is there on spin up actually has come to spin down. Okay, it is usually measured in -1. Okay, so we get an expectation of value -1. So what happens? Initially, it was in spin up, it was in 0 state, and we did something, and it has fallen into a rotation angle. Did something in the sense I didn't specify the parameter here, the theta here, but it did change, and we know that it changed, not because we're observing it on a block sphere, because we have an expectation value of -1 here. Okay, this is something I've been showing like always in the previous slides. So what goes in this is some rotations on these thetas. What are the thetas? These are the parameters which we are talking about so far. So how do I actually manipulate? How do I actually tweak these thetas? Using some operation, right? In this circuit model, we will be using these rotational gates. Okay, you're using Rx and Ry. So Rx is along x-axis of rotation, Ry is along y-axis of rotation. So we are performing this on the qubit, okay, on the first qubit, which if we observe as a simple example, we are not having multiple qubits, we're having just one qubit. This is the, if you want to just split the model, if you want to see the matrix of this particular Rx, this is the matrix of Rx and this is the matrix of Ry. So what basically is happening is this matrix is applied on this particular, I'm sorry about this, this matrix is applied on the particular qubit and this matrix is applied on the particular qubit at an angle or at a theta value of theta 1 and theta value of theta 2. So these are the operations we are performing on this particular qubit, and we are now trying to measure the expectation value. Do we get expectation value? Why I use this is because we are doing it in a computational basis. Okay. Yes. So it is quite straightforward that we will know that what theta 1, theta 2 will be to actually change the state of this first qubit. We will know what theta 1 and theta 2 is to change the state of first qubit. Because this example is straightforward example, I'm able to say that, okay, I know it. What if you have multiple qubits in your system? And what if you cannot actually use a pen and paper and draw this mathematical derivation for how a sigma z is calculated on this particular qubit? So that is when we say, how do we actually choose these parameters? How do we actually choose these parameters in order to optimize the circuit, in order to minimize the cost function? How do we actually do it? So here we consider multiple qubits here, but in our demo, we don't consider multiple qubits. We have a cost, we need to update the theta, and we need to show it. So there's something like VQC and NN. Why I wrote this is in Variational Quantum Classifier and Neural Networks, which will be led by Mr. Ganguly, you will actually know how multiple qubits will be working on this particular space. Yeah. This is a classical machine learning, which we know it is a very straightforward machine learning. You have a backpropagation algorithm, which takes you through this. You can calculate the gradients, you can update your parameters, you can have a function. This is what a classical machine learning is doing. When you talk about neural network, when you talk about deep learning, you have multiple layers. This is a straightforward thing which is happening. Okay, we are not doing any sampling or anything here. We just get an output, we calculate the cost, we update it, we send it. Okay, you've seen the first part of it, right? The data part. So how is this data part fed into this system? How is this data part fed into this system of quantum? You have multiple ways of actually feeding data into quantum. Okay, let me ask you a question. I think it's boring if I just keep talking. Okay, did we actually ever thought of how the data is actually being encoded in our computer? Did we actually think of that? Because we know it's in the state of 0 and 1s, and we know that, but what kind of methodologies are we using? What kind of application requires what kind of encoding? Did we think of all that? Did anyone think of it? I mean, I don't need answer specific, but did anyone think of that? Hello? Should I check the messages?
Yes.
Okay. Did we ever wonder that, is there any other way that I can encode the data into my computer? Because it's already fixed, right? It's a kind of a fixed modules. The gates are fixed. The universality is fixed. Everything is fixed here. But what we can do with quantum today is nothing is being fixed yet. There are a lot of open research. The hardware is changing. The software is evolving. So a lot of methods are there which we can experiment with. Okay. So when we say encoding data into a circuit, why do we need to encode data? Only once we have the X, we'll be able to use the theta's, right? So how does this X get into my circuit? How does this basically, how does this, okay, I think it's too far, fine. How does this F of X theta, X get into this circuit? That is what we're talking about here, which is called as quantum embedding, okay? We're talking about quantum embedding. So generally we consider Hilbert spaces here. Why do we consider Hilbert spaces? Just to give us that, freedom, that we have a lot of space. We can have this multidimensional arrays of computations. We can color the tensor products. It's just the freedom we get because it also involves the real part and the complex part of the vector. Quantum feature maps. We know what feature maps are, right? Quantum feature maps more or less are not the same, but they work. They basically take your data from your surface. It's how the SVM is working, and take into a higher dimensional array and then compute the kernels and then feed it back to you. That is how they work. So how do you actually embed the data into this higher state is something which defines your computational power. Am I right? So the crucial part of designing an algorithm, if someone says my algorithm is good, so you have certain measures how your algorithm is good. So that is when you know the computational power of it. So quantum embedding is a very important part of it. If somebody is interested in the research, I think this is a good place to start with. Yeah. You have a set of if you have a classical input data, you have set of X's, and you try to just put that classical data into your system, parameterized. We all know. When I say parameters, I'm not talking about in quantum sense. I'm talking about different parameters, like different features a data set has. Okay, it's very overlapping. The words are. So in a quantum system, what we have, you have n qubits. We have q nodes. Q nodes are nothing but which deal with these qubits. Okay, you have discrete and continuous variables. Like the same types of kind of data how you have in data mining, we have read about this. So we have discrete, we have continuous. Okay, and for every category, there are a list of embedding techniques. When I say embedding, when I say encoding, it is all the same. Okay, so state preparations, encoding, open research. Yes, that is where we are currently in. These are the different techniques which are used to actually encode the data. If you want to do an algorithm in quantum computing, first we wonder, right, where is the data? If we want to do the machine learning also, we first try to get the data. We go to Kaggle, we go to places, and we download the data and we simply give it to the algorithm, right? But that is not quite straightforward in quantum sense. So you need to use these encoding techniques actually to encode your data. There are different displacement, there are Hamiltonian, a lot of encoding techniques as well, which each packages will be offering. But what are standard and what we will be working on is amplitude and angle is good. We are not working on in this example because in this example, we are using it in computational basis, but amplitude and angle encoding are used actually in this variational quantum classifiers and neural networks algorithms. Okay, this is the straightforward circuit we have. Okay, this is straightforward. You have a state preparation, you have a model circuit, you measure it, You get a class here and you do this post-processing. Okay, this is a mathematical representation, this is a circuit procession. That's all, nothing difference. Okay, so we need to wonder how the state preparation is done, the SX part of it, how the state preparation is done. Once the state preparation is done, only then you can operate on those operations. When I previously said Rx and RY, the rotation, those are simple rotations we are applying. So how do we do this? You have basis encoding, amplitude encoding, and angle encoding, which here I'm going to say. In base encoding, you assume that your data is in set of binary strings. Okay, so for number of binary strings, we'll be taking the number of qubits. So what if today IBM is offering us 5 qubit at max as an open source for everyone at one point in time? What if your data is large? So you cannot actually use this base encoding, right? There comes, I am actually rushing about it. Okay, if you have, please stop me there. There comes amplitude encoding. When you deal with the wave functions, when we are dealing with pulses, basically when the hardware aspect of it, but amplitude encoding is basically you're trying to encode the data in the vector space. You have these vectors and the components, you're encoding it in the amplitudes. When I say, is it straightforward? No, it's not straightforward. But is it difficult? It is also not difficult as well. But this is something which is proven to have exponential speeds. I think Shores and Groovers have been touched upon, right? So yes, so we have exponential speeds using this amplitude encoding actually. So generally in quantum computing, you have to assume that your device is doing this for you. The QRAM, the quantum random access memory. How in classical sense, our RAMs are doing, whatever Intel or whatever processor RAMs we are using, those are actually doing all this job for us. But we assume that if we have an ideal QRAM, if we are there, QPUs, this is done by that QPU. If it is not done by that QPU, as a scientist, computer scientist, as I said, quantum aspirant, we need to actually use this. We need to actually take the data, use this encoding mechanisms, take the normalization, put it in superposition form, and then perform the set of operations. So this is all on us. Okay. So all you are given a circuit that the job is for you to do. Angle encoding is very straightforward. As I said previously, you have Rx, Ry, Rz, you have different rotation. You can just rotate the particular data set at which it is already there. Suppose you have like a data set with a continuous value like 1.5. You can rotate it with an angle at 1.5. It is quite straightforward. A slight variant to it is a dense angle rotation. Okay, dense angle encoding, which is, it takes 2n features. It assumes that you don't have n features and you have n qubits. It takes 2n features, so multiples of that feature. So in this sense, you can actually, the basis, it is a sparse matrix which we are getting. In this, we are not getting that. Okay, we can actually, it's not much scattered, but it is more near, and you can actually find the similarities between it. This is the next version of it. Okay. So yeah, so the last thing which I want to stress on is the question of what encoding you should use in this to get a quantum advantage. When you talk about quantum advantage, we talk about exponential, quadratic speedups. So to get there, you need to actually prove that your algorithm is providing this computational powers. To get there, you need to actually show that how you can work the circuit on. To get there, I think encoding mechanisms are very important at this point in time, and it is an open research problem. There's something called ansatz. If you have a best encoding, you can actually benchmark your ansatz and use it for other applications. For example, in machine learning sense, we know what is working, where it's working. You just import that particular thing. You just import NumPy and you say that it is working good in tensor because it is how multidimensional arrays are working, because it is already there and you're just making use of it. It is proven. Your job is to optimize it only for your data set. You're not concerned about how the data is actually being coming. You're not concerned about all that. If you're good at this, there's an open research problem. There's no empirical evidence, experimental evidence as yet. You can work on encoding mechanisms of it.
Ma'am, sorry to disturb. Can you please repeat that last one you mentioned about the? Actually, you went so fast that I did not catch up.
I'm sorry. Yeah. You particularly want to know about this open research problem?
You mentioned that how we can specifically just optimize for particular algorithms and then.
Yes. Okay. You want to know about Q and N part? This last point is, you're talking about this point or this point? Which one?
You mentioned about like how we can just specifically optimize something for our like NumPy
right.
or something. Yeah.
Got it. Ansatz. You talk about ansatz, right? Specifically optimizing ansatz.
Yes.
Okay. So you have an application. Okay, you have a data set. Do you do we actually know that which encoding technique is working for this data set? As of now,
No.
in quantum sense, we don't know that. What if, as a scientist researcher, you come to a conclusion that if I need to do this classification problem, I know this encoding works really well. It can actually accurately 99% of the time, it can classify dogs and cats to a different category. If you have come to that conclusion, what you can do it, you can see, you can benchmark your ansatz. Ansatz is nothing but architecture in which, starting from encoding to the measurement, everything you're doing it, right? So you can just benchmark that particular part of it. This is an open research problem I'm talking about in quantum neural networks. Yes.
And actually how we do this, like practically, like
Yes. So
how
when
this
the demo,
encoding is.
yeah, thank you for asking. So when we are doing the demo, I just show you those areas, okay? I just show you those templates and ansatz where how you can actually implement it, okay?
Okay.
Yeah. Am I running out of time, Mr. Darshan? Can you just confirm? Because should I go to the demo part first?
Yes, ma'am. Please proceed.
Yes. Can I explain the example, or should I just go to the demo?
No, you can explain, ma'am. Please.
Yeah. Oh, okay.
Yeah, please.
Okay. So, okay. Before we have seen that, right? This is something expectation value we got when you are trying to take a qubit, do two rotations in Rx and Ry basis, we get an output and we get an expectation value. So what do we want to know here? What are the optimal thetas? What are the optimal theta 1 and theta 2? This is just a mathematical, and I'm extremely sorry for the matrix. It's completely enclosing it. Yeah. So we want to know, this is our initial qubit state, which is in Z basis. Like this is the straight up vector spin up. We have done something, right? We did do something which made this particular qubit turn and flip into spin down state. What did we do actually here? So we have a data set which is like, okay, I'll talk about in classical sense now. We have a data set which is very clumsy. We don't know which goes where and what. You put it into a model. You give it to this machine learning algorithm. It all of a sudden gives you, okay, it gives you, you know what? This is the category 1, this is the category 2, this is the category 3, which I don't know. It is like an outlier cluster. I don't know what this is. You deal with it. That is something which it has given you. Right? You know this is initial, you know this is the final state. But what did we do here to bring this initial state into final state? It is something which we are going to talk about. Okay? Yeah. What if I don't know? So what if I don't know that what actually makes this initial state go into a final state? But this is what we want, right? It's a black box. I don't know as of now. I don't know what. I gave an input. Someone told me this is the output, and I got the output. But I don't know how it went actually. Okay. When we're trying to calculate this particular thetas, how do I know what I'm supposed to do in order to get an optimized level of an output? You know, how do I do it? So basically, we are actually using this gradient descent methods. If you have this slope, and it's a typical classical sense. We're not doing anything. I'm not talking about anything on quantum here. I will talk about how this descents are using in quantum in PennyLane, but in this typical classical sense, what a gradient-based method does is it actually gives you that local minima point of your application, whatever thetas, whatever parameters you're working on, it gives you local minima. How do I come to a local minima? How do I say that this is the best? When I do this, I'm sure that my model will give 98% accuracy, 99% accuracy. How do I do that? So say, for example, you have a combination. When I say theta, I'm not talking about one parameter. I'm talking about set of parameters in conjecture you can take, and you found that at maybe cost 0.3 here, this is something your particular model for now has given you the output or the measurement. What do? You try to minimize it, right? The minimum your cost is, the less your loss function is. So you try to minimize it. How do you minimize in gradient descent? It is like descent. It goes in one way. The shallower it is, so the negative way, the opposite direction, you can give any names for this. In the opposite direction, you try to step down. You try to increase your steps in your programming, but actually you're stepping down into the local minima of your optimization parameters. So where do you end up here? This is completely classical machine learning, okay? So where do you actually end up here? You end up here in this, where do you actually converge? You actually converge in this minima point. So this is the minimum of this, but if I'm modeling it, obviously we can't model everything here. If your data set is more, if you have much features, I can't just say this is the local minima of it. But I'm telling, ideally, this is something which you can do it if you have a simple example, okay? You have come to a local minima. Okay, is local minima good enough? When you're talking about training set, yes. But the end goal is global, right? For unseen data. So your training data, it is good. Testing data, it is good. So what if you have an unseen data? What then? That is when you have to induce lot of parameters, tweaking, updations. I think somebody asked me why we need to do it. This is where we need to do it to achieve that also. But as of now, we will not be able to do that in this quantum sense. Classical sense, we have already gone ahead of it. Yes. Okay, so how do you calculate gradients in quantum here? So there is something called as phase shift rule, which PennyLane is implementing. You take two circuits, okay? You know back propagation, how we do it in classical machine. You go forward, you go backward. When you go forward, you compute the result. When you go backward, you compute the result, and you take the difference of the results. You take the difference of the result, and that will become your gradient. So multiple gradients, multiple tweaking. That is a simple phase shift rule PennyLane is following currently, okay? What is PennyLane I'm talking about? PennyLane is something which is offered by Xanadu. It's a startup in Canada, Toronto. It is a software package for quantum computing. Qiskit is from IBM. It is also offering the same. Rigetti, it's a forest package is there, software package. QHash, we all know it's by Microsoft. Okay. Why did I give this link is because if you are interested in quantum machine learning variational circuits, if you are not sure where to start, this is the best place to go and to start from the projects which we are there, like how we started machine learning back then, like 5-8 years back. This is somewhere we might start. Okay. Now I'll just go to PennyLane demo. This is how we know partial differentiation is done by TensorFlow. Automated differentiation, which is also called as PennyLane, does more or less the same thing. How TensorFlow. If we have worked with TensorFlow in machine learning, we are good to go to work in quantum machine learning and PennyLane. That is something which I want to compare and say. How TensorFlow is Google, the same thing PennyLane is for Xanadu, offered by Xanadu. It still uses NumPy, what we know, for multi-dimensional arrays. It's just a plugin modules, okay? Yes, this is how our variational circuit is implemented in PennyLane. All the green nodes you are seeing are the quantum nodes, okay? Quantum nodes. And the orange color, if you don't see it orange, I don't mind. This is the classical nodes of it. You remember I said we take a circuit, half part of it, variational circuit. What is variational circuit? Half part of it is done, half or 60, 80%, it depends upon how you perform it, is done by quantum. The other rest is done by classical. That is classical quantum machine learning. That is how hybrid model we are currently in. So classical nodes, once you get the output, you're calculating the cost on classical node. This is calculated here. Once you optimize it, training, it is done here on quantum node. Okay. So whenever you find a quantum node, just imagine, there's a variational circuit going on in this quantum node. That is where your imagination should come into place. Because when we are programming, we are basically using these packages. Yes. Yeah, I think everybody is waiting for this part.
Ma'am, I have a question.
Yeah.
Yeah. Actually, you mentioned that we are doing this computation part on quantum node and then evaluation part on this classical node. So, does there like data transaction happens between quantum and classical? What exactly happens there?
Yes, exactly. That was a good question. Okay. So you asked about data transfer, right? Okay. I said we have a classical data. We are giving it into a quantum circuit. So what we are getting again is a classical data, right? Once we measure the cube, it will fall into one state. So that is the reason we are doing the sample probabilities and we are measuring that particular state. And we get a Y. That is a classical. So this classical data, we are again plugging it into this classical data. We are again plugging it into a classical machine to calculate our cost. And then from that cost machine, we're doing the same thing. We are plugging the classical data into a quantum machine. We are using the operations, but here we are using the updated parameters, not the regular parameters we have taken, not the initial parameters, but the updated parameters. So your question is, how do we do this transition, right? The transition basically is, the transition basically is back propagation, right? You just take from a quantum, you give it to a classical and classical to quantum. Okay. You can relate to machine learning model of this, right? So whenever these are there, just assume that these are the black boxes, like oracles you have. So you don't know basically what is going on inside it. But what we're trying to do is we're trying to open that file and see, acha, there is a variational circuit here. That is where we are coming into picture. We know what classical is doing, but we don't know what quantum is doing. So that is the reason we're talking about variational circuits here. Okay, the plugging ins here. I mean, yes.
Yeah, means I'm trying to picturize in one, like the whole thing. You mentioned that we are trying to optimize the circuit, right? And for that we are applying the quantum machine learning, and then with this optimization we are getting optimized circuit for the our work, right? That's what we are doing in bigger picture.
You're talking about optimized circuit?
Yeah, means what we are doing right now, like you mentioned that optimized circuit optimization, right? You mentioned on the slide. Yeah.
Yes.
With the every next step we are trying to achieve this same thing. Like we are trying to get into the point where we use minimum number of circuit for a specific task. That is what we are doing.
Minimum number of circuit. I don't know why minimum number of circuit in this. We're talking about parameters here, because circuit is it's fixed. We have fixed the circuit, the number of gates, the input, that is fixed part. We're talking about the parameters here. Parameters, yes, we keep changing. What is the optimal value of to give it to a particular parameter so that we'll be able to predict well.
Okay.
And again, a classical sense, predict the label well. So suppose.
Okay. Yeah.
Suppose in the testing data, in the unseen data, you see that, okay, this is the label of cat, but why didn't it fall into that category? Why is cat left as a cluster, an outlier? That particular cluster is left an outlier, but you want it to fall into a category 1, class 1, but didn't fall it. So what you need to do, you need to again go back and see where it is going wrong, right?
Yeah.
That is basically you're training it again. So the next time what happens is, whatever data you use, if it is cat, it will fall under class 1. If it is dog, it will fall under class 2. If you give some doll, it will fall under some outlier. That is what we want as machine learning people, right?
Okay. And how we are, it's like now we doing this transition from quantum to classical, and then classical to again quantum. So what if that means, like I'm sure like there will be a difference in encodings.
Right.
So how exactly that is being done?
Yes. So you're basically talking about this, right? Can you see my screen? Basically talking about this. Yes. Okay. So where are we starting at? We are not actually starting from quantum. We are actually starting from classical, right? So there is a classical node, which we are plugging into quantum. So which part of classical we are plugging into quantum is only the training part, right? So when we say training part, we are actually encapsulating this quantum node as a device. You're talking about simulator, we have these simulators, default qubit, default Gaussian. You're talking about the hardware, IBM is using the hardware, like it is Melbourne, SDR, different servers, different hardware. So it is, as a programmer, our, it falls under our responsibility to actually differentiate these nodes and then send it to the system. It can be a simulator or a hardware. Okay. I think if I just show you this. Okay. Are we good to go further?
Yeah. About this, you mentioned the simulator. That's where the problem means the doubt got here. Yeah.
Oh, okay. That was it out. Yeah. Let me know if you can see my screen. Okay.
Yeah.
So the same simple example which you're talking about, qubit rotation in quantum machine learning using a variational circuit. How we are doing it? Ideally, we suggest that, PennyLane, it's not me, it's PennyLane suggests that you take a different environment and import everything what you're importing generally in machine learning, you import it through PennyLane. That is what the suggestion is, okay? From PennyLane, you import NumPy. Don't directly import NumPy because they actually revamp these packages exclusively to work on quantum machine learning feature sets. So that is the suggestion which they give. So you can import the necessary libraries. I think this is where you're talking about generally. Quantum simulator. So to work on our data, when I say quantum node, it should work on quantum simulator or a quantum hardware. When I say a classical node, it should work on a classical server, classical system. So to get this quantum simulator, you need to create a device. Okay, these devices, there are a set of devices I had showed you in the slide of demo. There are a set of devices which are available with PennyLane already. Okay, you can just use those devices and mention the number of wires. So number of wires is nothing but number of qubits you want to send. In simulators, you don't have any limit, but in hardware, when you're actually using it, for example, IBM, it actually tells you how many qubits it has. You can't go beyond that. Okay. You can construct a Q node with your circuit. When you construct a Q node, I think this is where the transition you've asked about. you actually call the Q node. Because this is like a normal classical programming, you keep writing it. Unless and until you call the Q node and you loop this process, that will not be called. So there's a special mention. That is the reason I have commented on it. You create a circuit. The circuit we talk about, U of, X and thetas and all. Apply this 2 rotations, these are the operations, on 2 parameters. We take only 2 parameters here, okay? That is rotation X and rotation Y. On this particular wires and on this block sphere. And what are you returning here? We get that, right? We get that expectation value, sigma Z. What is sigma Z here? We are actually measuring it in poly Z, computational basis, Z basis. Okay, that is what we get here. We need to actually test. Okay, we did what we did, right? How do we actually test if the circuit is behaving as we want to behave? Let's just change some parameters, and see. Okay. So it's not converging to 1, okay? But ideally, when you say that expectation value is 1, that is when you know that, okay, there is no change. It is behaving as I want it to behave, okay? But what if I change it? It is changing. So cool. I just still give 0. So requires grad. When you're computing the gradients here, when it in the gradient descent, we set it to true because we are using this gradient optimizer, okay? In gradient-based methods, you have different methods, stochastic methods. In that, gradient descent optimizer is something which is already PennyLane is offering. If you know how it computes there, you will already know how it computes in quantum machine learning sense as well. Okay, so you basically construct this circuit. You see if the circuit is working well by giving set of parameters. And now this is the point which we need to talk about, right? We need to actually compute the cost. We need to actually compute the cost for this. It is simple circuit. So what we say, the circuit itself is the cost. We don't actually say that to get to this place, we need a different cost measurement. We don't give that. We take the complete circuit and put it into our cost matrix. When we're calculating it, it again goes to cost matrix. I show you, right? 1, 0, 0, minus 1. That's a sigma Z cost matrix. So it basically goes into this cost matrix. Complete circuit goes into cost matrix. NumPy, we know how NumPy works. It takes a set of array elements. So initial parameters, it is on us. You can ideally feel, acha, this is the initial parameters I would want to give. Initially, we need to set the data, right? Initial parameters, let me set it to this level. You can set it anywhere. It is pi to minus pi. It can lie anything in between. And you calculate this cost of this initial parameters. This is where you get it. 0.8. Okay, better, but it's not good enough for this because we already know where cos theta 1 and cos theta 2 are lying. So 0.8 is a good thing, but we need to converge at some point in time. You know that descent, we have it. It should converge at some point in time, and that is the ideal optimization value we are looking at. So how do we do this? Optimize the circuit cost function using this particular gradient descent method. You just call it using QML. You know QML we have put it in PennyLane. Why do we give the step size? Just imagine that we have come to a place we have number of qubits, number of features. Should we go step by step? Should we go like every step I need to calculate? Or you have an idea that I can give a step size of 0.4, still I'm good at reaching the optimal length. Okay, so 0.4 ideally is a good step size for this particular program. We don't require 100 steps, but this we will see. It will converge before it, but we have taken 100 steps because it is step size of 0.4. That is the jump we have. Yes.
We can hit and try like that way, no? Means suppose if we don't know how many steps we require, we can just guess and then again modify next time.
Right. We can also do that, but in this particular simple example, because we already know it, we are not giving the trial and error method. But normally in a machine learning concept, we can actually try and see. Once the cost is increasing, we say, okay, we'll come back and we'll do something about it. Right. Yeah. Okay. So parameters, we are just setting it to the initial parameters, whatever we have. And this is something we are looping it, right? We are calling this particular circuit multiple times and to see where it actually converges. We are giving the cost and we are giving the initial parameters and we are actually, okay, this I think I don't have to explain. We are actually trying to do in this loop is using this particular step size. We want to calculate the cost at every 5th step. That is what is happening here at rotation. So, okay, we need to observe that what output we are getting it, because when we know the data set, when we know the output, we will know what data set it is, what cost function is doing. Here, it is cos theta 1 and cos theta 2. Theta 1 and theta 2 are nothing but the angles at which we need to rotate the qubit, which is in state 0, and it is going to a different state once you apply something. Okay, these are the different angles at which you need to rotate. And if you observe at 25th step, it's trying to converge, and then there is no change. Okay, basically your model is not learning anything again. So are you convinced with this? Are we convinced with this? Are you convinced with your application, your data set? If yes, because here in this sense we know that rotating at this particular angle in theta 1, rotating at this particular angle at theta 2, we know that the spin up qubit will go to the spin down qubit, okay, which we are not doing anything about it. Just by giving the initial parameters and calculating the cost function, we have concluded that this is something which is going to happen. If you're satisfied, if that is what the cost convergence you want, good to go. Once there's an unseen data, you'll also know the global minima, and then you can decide for yourself. But because it's a variation circuit in quantum sense, we're not going to there. I think Mr. Srinjoy will touch upon that in phase shift of VQC and VQNN. Yeah. Just anything left out? Okay. I think good to go. So these are the software frameworks. Yes, I should touch on this. Xanadu. I think you've asked, one of the participants have asked how you do it. Yes. So yes, this is something how we do it. We have the plugins for each and every machine learning general packages. So we know how Amazon is working. We know how Qiskit IBM is working. So if your code is in any one of the software package, you can actually plug in it into the PennyLane plugins. Okay, how do we do it? You can just, yes. Everything is there on PennyLane, okay? NumPy or TensorFlow. There is also JAX because you don't want to calculate the partial derivatives. If you want to do that, you can also use JAX. You can use PyTorch. Anything which you are comfortable in machine learning classically, that is already present in quantum machine learning packages. That is what I want to iterate. Yeah, I think I have only taken 10 minutes more. Yeah, I think that is it. That is about it. If you have any doubts, please feel free to ask. Yeah. Do you ideally type or unmute yourself and ask? I'm not sure.
Participants, please unmute yourself and ask your doubt. If you have any doubts, please ask.
Ma'am, you mentioned about that encoding, like basis encoding, amplitude, and angle encoding.
Yeah, I did.
Yeah. So, means I don't means like I'm just trying to connect. In yesterday's, I think in Srinjoy sir mentioned that we convert from basis to angle encoding with Fourier, something like that. So this is something similar to like what we do with Fourier transformation, right? In our digital signal to classical signal. So this is the same thing, right? We're doing with this. I'm just trying to.
Right. I think Srinjoy already touched upon this part of it. So why do we actually go for quantum Fourier transformation is to get this speed ups, right? So you need to actually encode your data. So it is always good in as you said, in amplitude encoding, and see if there is a speed up. Base encoding, it is quite not suggestible, but there are experimental evaluations which are going on. But what is suggestible is amplitude encoding in wave functions, because basically QFT gives you those wave functions, right? So I think amplitude encoding is good to go there. Because as I said, it's an open research questions. It should be it should lie with the scientist or the experimentalist who are doing it. Yeah.
So is it hardware specific or means it's a logical issue means?
Yeah, it's actually a good question. So what IBM also had the same thing, should we go with the hardware specific or should we go with, just the logic of the program? So what they've introduced is this pulse manipulation. So you can actually go, it doesn't actually reflect on your logic, but you can actually go and modify the pulses. When you modify the pulses, what happens? The amplitudes also get modified. When you modify the pulses, which are the qubits are being rotating in the circuit, the amplitude also will be changing according to it. So maybe they think that you can come to a good convergence in this using the pulses and the amplitude both put together.
What is pulse, man? I'm not able to answer.
Okay. Quantum pulses like this microwave functions. You can actually have these pulses manipulated. For example, in the classical sense, you have given this universality Turing machine. You need you need to have this gates, and gate, not gate, and you can measure anything, right? So whereas in quantum sense, they think that you can actually change the pulses of these gates to suit your operations, to maybe increase the coherence time of your qubits also. When you increase the coherence time of the qubits, what happens? Ideally, your output is also optimized. You will get the measurement level. So at the pulses level, your question was, it is to deal with pulses or not? Yes, it also has a major part in it, but not many are exploring that aspect because IBM has introduced it in pulses. Yeah.
Yeah, and like a common user, somebody like someone we have referring. So like
Yeah.
users like us, how we do that? With Pennylian, or is there the functionalities available?
Should I just put this in the link? So IBM Pulses, it's like everybody can access that. I think you need to write to this IBM guy, IBM Pulse. I'll just put that link. Okay. So you can access this IBM Pulse, and if you have a IBM Q account, I think you're good to go. Today in IBM, you can also create your quantum computer using IBM Metal. IBM is like, it's open. I'm not promoting IBM or anything because I'm an educator, but I'm just suggesting that whatever you want to explore on IBM end, you can do that. So wait, IBM Pulse one. I'll just put this link. You can just explore. Yes, I got it. That's correct. Cool. Control-C. I think you should find it here. Yeah.
Thanks.
Okay. Okay. Okay.
Hello, ma'am.
Yes. Yes.
Ma'am, what is this IBM Educator certification or program?
Okay. So IBM Educator certification is okay. Should I start? Do we have time? I'm not sure, but if I have, I can proceed and answer the question. Okay, fine. Fun. IBM Educator program is something. If you want to have access to these IBM machines, or if you have set of people whom you want to educate on this by using this IBM. Suppose if I'm giving you a demo, I want to have this IBM hardware specific to this particular purpose, right? I want to actually allocate it, reserve that particular part on behalf of IBM. So if you're interested in it, you can actually apply it, and IBM will look into the profile and proceed with the required details. There is everything is IBM Educator program is there, IBM Researcher program is there. Yeah, so I'm also an IBM Researcher program student. That is also there. You can actually apply to it. Okay. So
Okay, ma'am.
they will give you a dedicated hardware to work on your experiments, because not all experiments just require 5 qubits. You know what I mean? So if you
Right.
want to have that scale, you can actually write to them and they'll ask you a proposal, and you're good to go with that. Yeah.
Yes, ma'am.
You can also do the certifications, which we are doing for Qiskit developer certifications also, which will also give
Okay.
you scope. Yeah. Should we?
Ma'am, one last question actually. It's not technical. I just wanted to know, is the same thing happening with Qiskit and QHash? They are doing the developer program that happened with Azure and AWS programmers.
Okay. Okay.
Is it the same thing?
So you're talking about particularly to quantum, talking about particularly about quantum machine learning.
Yeah, you mentioned that Qiskit developer and then again the other developers. So is
I
it the same thing happening with the what happened with the Azure and AWS? For the promotion of their own cloud, they were offering their developers program like AWS certificate and all that.
Yes, actually, it's promotion. It's not more like promotion. I would want to put it in this way, like bringing awareness to this technology. So we have a lot of capable people who are working in these domains, but they actually don't know what these guys are offering. So IBM being globally recognized MNC companies, so they come up with all this. If you're interested, you can also join in the summer school of IBM, which is starting in July. But whereas, as you asked, PennyLane and these are all startups. Xanadu, these are all startups. They don't offer the certifications and all, but they are promoting. They are actually putting their content, experiments, everything on their websites and blogs for you to see. What is the difference? So mainly your question is: do you have to go choose IBM over Xanadu or Microsoft over IBM?
Yeah. Means like for the if their community grows, so it will help. For them actually. So it's a kind of thing like if the AWS certifications in like the people who uses AWS increases, so the use of cloud of AWS increases in that
Right.
sense.
Yeah, that is that. That is it. Okay. As a AWS business architect, I know how this is, but I think yes, IBM also wants everybody to come on board and work on this quantum computing. You never know, right? We have these hacks and all happening. what if you are a student who have that potential and you are somewhere in a remote place of India, IBM actually want to know who you are with your result. So it just is asking you to submit the results so that it can look at it. And it's not just one way, okay? If they really like, they're actually giving as Qiskit advocates. There is a program called Qiskit advocates. They will ask you to come on board and work with them. So it is not like they just promote and they want everybody to know the technology. They're asking people to show what you got, and you're welcome on board as a researcher, as an advocate, as an ambassador, different programs. I think IBM is doing wonderful job on this aspect of student collaborations. Yeah, and it's recently been collaborating with IIT Kharagpur, IIT, IISER. I think everything is being done. Yesterday there was news of IBM collaborations. You should check out IBM blogs. What I'll do is I'll just link out everything and I'll give it to your coordinator. Maybe he can, circulate on this. Yeah.
Yeah.
Okay, are there any other queries, participants? Okay, I hope there are no queries. Okay, so thank you very much, ma'am, for being with us, for sharing your knowledge, your work experience with all of us.
Thank you. Thank you so
Thank you
much.
very much.
Yeah.
Thanks a lot. Thanks a lot for being here.
Yeah. Thank you. Yeah.
Srinjoy, sir.
Hello.
Hello.
Hello. Yeah. Yes, sir.
Yes. Yes. Okay. Okay.
Am I audible, sir? Am I audible?
Yes. Yes. Yes, sir.
Oh. All right. So maybe we can begin, sir.
Yes, sir. Please.
And yeah, thank you so much, Miss Gopika, for that wonderful presentation. Like, I think she covered everything in detail, and I hope that there are not so many doubts, because the main thing which I want everyone to understand is just quantum machine learning is very new, and this is an advanced subject. So what I assume is that whenever you are taking this subject, everyone has an intermediate level understanding of machine learning and quantum computing, both the subject. So intermediate means not the fundamentals of a qubit and all those, but even quantum algorithms, just as we covered on our session 1, 2, 3 on 26th, I think. Yeah, on 26th we covered the 4 advanced quantum algorithms and the basics of quantum computing. That knowledge you should have, plus you should also have basic intermediate level background on machine learning. Intermediate means you should also be familiar with some deep learning stuff as well, that how deep learning is working, what is a neural network, what is a loss function, what is a cost function, all these, what are the optimizers, how these things are working. Because I'm not going to go into very details, these are separate topics in themselves, so I will not go into those details, that how that Adam optimizer is working or how some other optimizer is working. That is a part of a machine learning curriculum. I will only touch upon the interdisciplinary aspect where the quantum and this classical ML is combining. That is the only stuff which Ms. Gopika has connected with all of you, and I think she has done a wonderful job. She explained with all the details how the things are working, and a small demo you have all seen. So my stuff will be kind of a bit of repeat, not like too much repeat, but yeah, I will also show you 2 demos. It's not like that, but the concepts which you just now learned about variational circuits, those will be similar. So let us get started. Sir, so I'm can I start, sir?
Yes, sir, please. Sure.
Okay.
Yes.
Okay. So is it visible, sir?
Not yet, sir.
What is it showing, sir? Like maybe.
You are presenting to everyone.
Oh,
Start.
yes. Then it's visible, sir. Like now it may be
Yes,
visible.
yes. Now it is visible. Yeah.
Okay. Yes.
Yes.
So yeah, welcome everyone to session 4. And let us go ahead. I will talk about briefly about quantum gradients. This you already know. Miss Gopika has covered in a very nice way. And I will just give some brief maths steps. That's it. And then I will show you the only demo of quantum gradient calculation, a single demo. And then I will show you a variational quantum classifier, which you already saw in Miss Gopika's session, variational circuit. And then the diagram which you saw where the quantum circuit is there, the state encoding, then after encoding cost, then cost goes into the optimizer, and then again the parameters are fed back into that is the actually the variational quantum circuit working, which you saw in the slides. All right, I will draw the diagram again. All right, so let us get started. Again, just like our last session, I will be writing things down because in this way I feel that many are comfortable and they get to understand the things in detail. So let me see if this. So gradients, so let us start with the notion of classical gradients. Let me give you a motivation how the quantum gradients come into picture. Let us see first classical gradients, because you need to know the background, even though you know, but you need to appreciate how it actually came, isn't it? That is the proper way of learning, that how that thing came. You should know the past, you should know a little bit of history. So this is the history. Dy by dx, we all know that this is the derivative of y with respect to x, has this formula in limit form. This is just from high school. This is nothing new, but look at this formula very carefully, because these foundations have actually helped to create the rule for quantum gradient differentiation, like quantum gradients. That's why it is necessary to look at this carefully. Okay, what is happening? You shift by some small delta x, okay, which is infinitesimally small. And then you subtract the function fx. That is how you calculate the gradient. So gradient is nothing, but it is like a shift. It is like shifting. That is why now we will use this same intuition for quantum gradients. How? Then the quantum gradients formula we can define in the following way. Quantum gradients formula on the basis of this formula. On the basis of this rule, we can define, and the formula is known as parameter shift rule. The phase shift rule, which Miss Gopika was mentioning to everyone, that is this one, parameter shift rule. This is the rule which is used to calculate the gradient of the quantum circuit. So how is this formula related? This you can denote it like this with some parameters and an observable. So observable may be your position, momentum, or anything you want to measure. So that may be the observable B. Okay, so B is observable. Okay, let me write B is what? B is observable. What can be the observable? It can be anything. You might be measuring some quantity like maybe position or maybe momentum you are measuring. So it can be any quantity, observable. And what are these observable? How do you denote them? Observables are denoted by operators. And I have defined operators in our last session. What are operators? Operators are just transformations in the Hilbert space, and they can be represented by what? Matrices, because matrices also represent transformation. That's one. So consider this as a matrix operator. And with respect to theta, then with respect to the parameter, you will shift the parameters. So start shifting the parameters with respect to this matrix, of course, because you are measuring with respect to this observable. That's why you have to include this, and this is known as expectation value. Okay, whenever you have these brackets, something, an operator like this, then this is known as what? Expectation. That means the mean value, the average value, expectation value of that operator. Then what will you do? You just shift. You will shift it by some phase. And again, minus, look at this formula. Compare this with the classical gradient carefully. This formula is very, very same. Only the presence of observable is there. Apart from that, it is just shifting. And also you may ask, why are we doing this? Because in quantum machine learning, it is, the term is quantum machine learning. That means we have to calculate gradients at some points to. Can we do it in a quantum friendly manner? This is the way to do it in a quantum friendly manner. So this rule. This rule is quantum. This is a quantum friendly. This is quantum friendly manner. You are doing differentiation of or gradient of quantum circuit. And in a more compact form, if you want to write, you can write like this. If you take a function which is your quantum function, what is a quantum function? Just quantum circuit. We define in PennyLane as a function. We just define a function and we just mention the gates, the rotation gates, which are parameterized by theta. So like that. So then what you will do, f of theta 1 minus f of theta 2, a much more compact notation. This is a more elaborate. This is a more elaborate notation. And this is what? A more compact notation for quantum gradient. Okay, now you would like to see an example. How will we see that example? So let us take a very simple example, that f of x is equal to sine x. And I want to calculate the derivative with this rule. This one. This rule. This is the main formula, that's why. So what we will do? Then f dash of x will equal to, just I will put into the formula, half of sine. This is a very simple case, x plus minus half sine x minus, and this rule gives you the results approximately, not total accurately, but approximately. Okay. What will be the next step? Half is already there. Then what with sine x plus pi by 2? It is cos pi by 2. Isn't it? Minus of, what is sine x minus pi by 2? Minus cos pi by 2. Now you can see that we are getting sine x derivative is cos x. We all know this from high school. That means half minus minus will get plus. That means you will add them, cos pi by 2 plus cos pi by 2. Which will be what? Half 2
pi by 2.
cos pi by 2, and then you will get the result cos. So approximately you are getting the result sine x is equal to cos x. This will all happen approximately because nothing is accurate, because this parameter shift rule is just based on the classical gradient method. That's why it is approximate, but it will give you, but it will get you closer to the result. So now an important point, now some important points. So please note down the important point. The same circuit can be used to compute, that means same variational circuit. The circuit is variational. Assume that the circuit is variational. The same variational circuit can be used to compute both the quantum function and the gradient of the quantum function. Next point. Partial derivative of f of theta can be expressed as a linear combination of other quantum function. These other quantum functions use the same variational circuit, differing. This is the same thing which we did above, only in words, differing only in a shift of argument. Okay, so that's how we can actually calculate the quantum gradient. Now let me just introduce the basic notion of variational quantum classifier, and then I will show you the demo. So I hope that there are no doubts in this concept. This is very straightforward. I just took the motivation of classical gradient and showed you that, yeah, the parameter shift rule is based on that, and
Yes.
we can create it like that. Yes, sir?
Yes, sir.
Okay, okay. I was just like, I will just see here, like, maybe you can all type in the chat box if you are comfortable with this phenomena.
Yes, sir. Go ahead, please.
Okay, okay, thank you. So let us, yeah, okay. So now variational quantum classifier. So actually you have seen all the materials, so I would not like to repeat too much, because actually this session for me is actually short, because Miss Gopika has covered all the things wonderfully, and those were the actually basic things which you were know. So I will just give you a motivation. So let me give you a motivation. What is a classical? Let me start from a classical neural network to give you a motivation, and that is how I teach this subject. You need to take motivation from the classical one, then only you can build up the quantum one. So classical neural network. So what you do in a classical neural network, I will not go into deep, but for example, you have some inputs, and then maybe you have a layer, you have some neurons. Okay, these do what? These do the averaging operations, just a linear combination. Then maybe you have another hidden layer, and then you have some output. So maybe you can connect them.
Pardon, sir, but there is one query.
Yeah, yes, ma'am.
Sir, in neural network, we are having 3 or 4 layers generally, what we have seen. Okay, but is it right that when we study deep learning, then deep learning is nothing else, but it is generally the increasing layers, number of layers when increased, then it is called as deep learning. Is it right?
Yes, ma'am, exactly. Like there are two types of learning. One is the shallow learning,
Mm-hmm.
where you have only a single layer. And as soon as you start increasing like 2, 3, 4, then
Mm-hmm.
you start calling it a deep learning method.
Okay. Okay.
That's the, yeah, difference. So shallow is like, it will not work so nice. It will
Mm-hmm.
not be able to capture the underlying dependencies present in your data.
Mm.
But for deep learning, it can actually represent complex functions.
So it means
So it can actually capture, yeah.
deep learning is completely under your neural network because deep learning is
Yeah, neural networks,
algorithm
yes,
based.
yes, exactly.
Okay.
Exactly, ma'am.
Okay.
Deep learning, like it became a separate branch actually. It is a subset of machine learning, but it became separate because when people saw that neural networks are actually giving much more nicer results than SVM or random forest and all those algorithms, then they started moving towards deep learning.
Okay. Okay. Okay.
So it happened like that actually.
Okay, sir. Thank you.
So is that clear, ma'am?
Hanji, Hanji, Hanji. Thank you, sir.
Okay. Thank you, ma'am. Okay. So yes, so we have this. Then yeah, maybe I will not connect everything, but yeah, just assume that everything it is fully connected here. Okay, it will go here, it will go here, like that. Okay, everything is connected and the inputs are also connected like that. Okay, so these are inputs. This is, let me denote by H1. This is H2. That means hidden layer 1, hidden layer 2, and this one is output. So this actually gives you the, you can say, predictions. So if I just give a image, maybe an image of dog, and then it should say that whether it is a dog or whether it is a cat. It's a simple example. I just want to motivate you how this is, how you can actually getting to that point. Quantum machine learning, how is it getting started from the classical ones? How people got the motivation that yes, quantum machine learning should be a field to study. So this is how it started. So you have classical neural network. Now what they did, because they knew that they require quantum embeddings. Why quantum embeddings? Because quantum computers cannot deal with classical data. They are like, they are not even like vectors or nothing. So they do not live in a Hilbert space, but quantum computers live in a Hilbert space. So we have to go to Hilbert space, isn't it? Then only we can work. So that is what we do in encoding schemes. Then we apply encoding schemes. What are encoding schemes? Which converts your classical data into a quantum state so that it lives in a Hilbert space. So when it starts living in a Hilbert space, then only you can apply quantum circuit and all those gates and everything. Because remember, quantum computing is unitary. So that means you cannot work with classical. You need to have the number of inputs. Again, the same concept. The number of input is equal to number of output. The same things, which I told you last time, the same things happen. So that's why you have different encoding scheme. And Miss Gopika has already given a nice introduction, such as amplitude encoding. And I think I remember like maybe this angle also, angle. Okay, so these are like most common ones. And I think someone was asking about QFT and something encoding. I don't know who was it, but someone was asking.
Yeah, I was.
Okay, maybe. Okay, Ravi Raj, you were asking, I think.
Uh,
QFT. So is that doubt clear?
yeah.
Okay, this is not QFT. Okay, this is not QFT. QFT is something different. You are changing basis in QFT. Here I am not changing basis. Here I am encoding. Remember that. This is not basis change. I am not going to Fourier basis. I'm encoding. Is this part clear?
Yeah.
Okay. Okay, great. So that is why and then once we now, since we are in the Hilbert space, so once we do that, we are in the Hilbert space. So now our classical data has gone to Classical data has gone to Hilbert space. So now I can apply any quantum circuit I want. I can apply any quantum circuit I want. So since they are living in Hilbert space, that means I can now fed them into a variational circuit. Okay, a variational circuit. What is a variational circuit? Variational means a changing circuit. Okay, what is the meaning of variational?
The one changing
Variational
regularly
means
at a certain
changing
frequency.
regularly, isn't it? Yeah, it is adapting.
Yeah.
It is adapting or changing. So
Or
where in
shifting
classical
also.
it is changing. In classical, these are changing. Weights. Maybe let me call this W1, W2, W3. The weights are changing, isn't it? And after that, we also have a bias. So assume a B bias of B. This is a bias. Also assume that we have a bias as well. Just like, normal machine learning stuff. Okay, so we have these weights, and these weights, these W1, W2, W3, and this B, all these parameters are variational. Why? Because they change. How they change? Because of optimizers. And that is how you got this name, variational circuit. That means a circuit which has these kinds of parameters. But since it is a quantum circuit, that means we can have parameters in terms of either like yeah, in rotations. So that's why maybe you can build a circuit like this. So this is a general phenomena to implement. So you have the states going. So maybe you have some qubits. First, you apply some state preparation. Okay, state preparation is nothing but that encoding stuff. So you prepare those states, so that they live in a Hilbert space. State preparation. Then you go to your circuit. Okay, then you go to your let me say u of, let me say, theta1. Then maybe you want another layer. Let us make an analogy. Maybe you want another layer. So let us make this circuit like this. Maybe you are doing a complex task using quantum machine learning. For example, cardiac, like, cardiac disease detection. It is also a complex task. So for those, you need some nice amount of layers, isn't it? Theta2. Okay, and you can add maybe more layers. I will not add here. I'm just giving you an example. And after that, you take some measurements. Okay, you take some measurement. This is the symbol of measurement, as we all studied before. And then finally, you get some outputs, and those outputs are your predictions. Now compare this circuit, this part. Compare this part. Input is here. Input is coming here. The classical data is coming here. Okay, the classical data is coming here. Then it turns into quantum state, something like, psi1, psi2, or something like that, maybe psi3 up to psi n, or in anything which you say. Then we apply this. Okay, so then we get out a function, maybe f of x dependent on theta1. What is this theta1? This theta1, and this is the analogy which I want to make. This theta1 is comparable to W1, the classical weight which I showed you. That means this u of theta1 is your hidden layer. So this is actually h1, but in the quantum domain, and this is actually h2. Now are you getting the point? I am just giving you a motivation. You know all these things, but I'm motivating you. How we reach this stage actually.
Yes, sir. Yes, sir. Very nice. It is
Okay,
actually
ma'am. Thank you. Thank
leading
you
us
so much,
to
sir.
a right
Hmm.
direction.
Yes, because ma'am, because already we should always know the motivation, how the things actually came. Once you know, then you get the interest to study that subject more and explore. So that is what I'm just giving, because all the other concepts you actually already know. So there is nothing more for me to teach. So I can just give you a motivation, how you should proceed with this field. Okay, and this is measurement. We all know that this is measurement, and why I am also teaching this is because the same kind of circuit I am actually using in the variational quantum classifier demo. That's why. Even the quantum gradients which I covered, the same kind of code you will see, just like the last session. Just developed the circuit and just showed you the code representation. It's the same thing. Okay, so this is the, like, main motivation, and this is like what people also called a quantum neural network. Okay, this is why they call, because now you know why they call, because these PQCs, okay, these are also known as PQC. So maybe this is PQC1, PQC2. What is PQC? PQC is another name of variational circuit, which is known as parameterized quantum circuit. The name also makes it's parameterized. Theta are the parameters. Theta are the weights which gets modified by the optimizer. Okay, parameterized quantum circuit. Okay, what also, yeah, okay, quantum neural network, and then I will just give you that, like, maybe I should connect the previous things, like, okay, so maybe, like, now remember that analogy which Miss Gopika showed you in the slide. These predictions now come here. Okay, these predictions, okay, and dot like this, it will come here like this. Okay, it will come here like this. Okay, where it will go, these are the predictions. So let me denote them, maybe y hat. Okay, y hat. Okay, where it will go into a cost function, isn't it? It will go into a cost function. This thing you have already seen. I am just giving you the motivation, the circuit diagram. It will go into cost function. What will the cost function do? It will calculate some squared loss, maybe y minus y hat. What is y? Y is true label. That means we are high. And also, yes, we have assumed that this is supervised learning. Okay, let me mention this point. This is supervised learning, means the data has labels. That's it. Supervisor. So
So
who is a supervisor? Is a
is
label.
it not applicable for unsupervised learning?
Unsupervised, currently there is research going on, and currently, like, mostly this is for supervised, ma'am, not so much for unsupervised.
Okay, sir.
Because in most of the, like, industry also, we are using supervised only, like mainly is supervised. So that's why I am giving you the notion of supervised directly.
Okay, sir.
So
Okay.
okay, yeah, thank you, ma'am. So this is the true level. There is a predicted level. So you calculate the cost. Okay, let us also write a square. So squared loss. Actually, we are using squared loss in the demo, so that's why I'm giving you. But there are other loss functions as well, like exponential loss or tangential loss or maybe savage loss, and yeah, there are lots of loss functions. I won't name them one by one, but yeah, you get the point. What we are doing, we just calculate the cost and then we give it to the optimizer. Okay, optimizer can be anything. Optimizer may be your optimizer. This is the optimizer. Okay, and the optimizer throws out these, actually. Optimizer throws out where is it? Yeah, and it goes back to the circuit again. It goes back to the circuit again. What goes back to the circuit? These things, theta1, theta2, optimized. These are now a bit optimized. And what are the, this is we use the squared laws. Here we use the square laws. Just for completion sake, I'm just writing this. And optimizer, you can have maybe the one which we are using is like momentum based, so it's like Nestro momentum in the demo. I'm just giving you the name, but maybe you can also try with Atom. And I have provided you the link in the notebook, actually, and you can explore by yourself. It is in the documentation, and I also urge you that you give it a try. maybe use different optimizers and check what results you are getting. Okay, Nestro momentum, Adam is also momentum based optimizer. Then maybe you can use gradient descent. Okay, stochastic gradient descent. Stochastic gradient descent different from gradient descent. Okay, in gradient descent, you take the whole batch of trade, isn't it? You take the whole batch, and stochastic gradient, what you take? You take one by one. That's the main difference between gradient and stochastic and that one. Okay, so yeah, I will not go into machine learning stuff. Okay, again, that requires dedicated time and dedicated study. Machine learning is a big thing. So I will just give the intro.
Using the
Mm.
simulators, we can
Mhm.
do all these. We can cross all these phases.
Yeah, actually, ma'am, what happens is we will be using the simulator only for this part. Only for this part, this quantum part, this
These
one. So this is,
when we are passing the theta values or when we are
yeah,
calculating
yeah, yeah,
cost and
exactly.
optimizer, all these things will be requiring a simulator.
Yeah, quantum simulator. This is a good point, ma'am. Thank you. I will write this. Okay. This is actually also an important point I wanted to mention. This will be quantum simulator. Then from the measurement part till all these points which you see, like this measurement. Okay, let me write clearly. Like see this measurement. Okay, then this cost,
Okay.
optimizer. These are all carried out in classical classical computer. So quantum computer is only a very small part, you can see. It's only that circuit. So that is why this is also known as hybrid. This is known as hybrid classical quantum. And if you remember, I also mentioned this concept in Shor's algorithm. Does anyone remember? I mentioned in the end that Shor's is also hybrid. It's also a
Yes,
classical quantum.
in on the another day when you gave lecture, that at that time you talked about shores.
Yeah. So they are also defined. Okay, I'm getting into how the initial chain of theta values. Okay, sir, that will be just random. You can just randomly initialize them between value 0 and 1, just like you do in classical training. Actually, it's not much different. It's not much different. You can initialize them randomly, the thetas, and then you start optimizing it using the optimizer. Just as we initialize the neural network weights using some random value, in a very similar way we can do that. So I hope that it is clear. Okay, so but also yes sir, yeah, thank you sir. Okay, this is hybrid classical quantum. Okay, where is this?
Classifier.
Yeah, maybe actually I was about to write a mechanism, but I think, sir, you gave a good word. Yeah, maybe I should write classifier.
Thank you.
Yeah, thank you, sir. Really, it's yeah, that's more nice word, classifier. The mechanism is the mechanism is like classical plus quantum. Some quantum stuff happening, then all the other stuff classical. But most of the part will be classical. You will see. So you might say that okay, this is not useful at this stage, or might be like that because we do not have actually the proper quantum hardware to test this. And the examples which I will show you, they are also like very like elementary examples. And the reason for that is because this is a very new field. This is a very young field. Maybe it's only been few years, like maybe it's only been like 3-4 years or something. This field is developing, and it takes some time to develop these fields. But also it is also dependent on the hardware. So the real power, actually, let me mention this, that the real power of QML, the real power of QML will come when the data sets are very large. Data sets are very large, actually. That is how you will get the real power. Now you cannot take very large data sets and run it on a quantum computer. It will give you very bad results because all the hardware is noisy and they are subjected to decoherence. So that's why the qubits are very fragile. So they are not stable. So that's why it is not good to try it. And yeah, and also apart from that, especially the IBM hardware, they are very busy. Like even like maybe your job will be like, even if you send the job to the quantum computer, it will go into the cloud, it will go to the computer, but it will be queued for a long time. If there are like 50 60 jobs pending, then like those 50 60 circuits will take their own time to run. And then maybe like you have to like wait for hours, maybe 5 6 hours even, or maybe a whole day to get your circuit run on a real quantum hardware. That's why we take the help of simulators. That's the reason. So that is the first reason, and second is the noise.
So simulators, see, actual
Yes, ma'am.
hardware is sensitive to noise. Okay, but simulator is not so sensitive with noise, right? But a researcher will never be able to find out the actual results because of absence of hardware.
No, ma'am,
So
it's not like
research
that.
can be.
No, ma'am. The simulators which we have, they are like a replica of quantum hardware. So they actually inherently add some noise to your experiments so that it can simulate like, closer to a hardware. Not exactly,
Oh,
but closer.
okay. So research
Yeah,
can
yes.
be.
Yeah, research can be done.
Okay.
Research can be done. Yeah, you don't have to worry. You can do research, and even you can add your own noise as well. There are methods in Qiskit. I will not be covering them. That's some other stuff. Yeah. But there are methods with the help of which you can actually add more noise to your experiments to actually get a real, like, hardware kind of effect in your experiment without even using the hardware. So like that. All right. So I think I have developed enough. Yes, sir. Yes, sir.
You're telling about when data sets are very large.
Yes, sir. Big data.
Can you
Big data set.
quote some instances, real-time instances where
instances? Maybe you take a data set of
large
maybe
data sets?
large data sets. Maybe like you can take a data set of COVID-19. There are lots of complex images in COVID-19 data set, and maybe large data set, maybe like like 20 or 25,000 images, like that I am talking about. That may seem small to you for classical ones, because in classical it is very perfect. We get nice results in classical, but in quantum again, it's not necessary that you will get noisy results. Is there any emulator? I think you are mentioning about simulator. Yes, we do have simulators, and I will be showing you a simple PennyLane simulator, and I have also provided you a link where you can try various plugins. Miss Gopika showed you the plugins, so those plugins you can try, and those simulators of each other, like other companies like IBM or Rigetti and all those companies, you can try actually. So I hope that is clear. Then I will be moving to the demo.
Can we apply smaller data sets to simulators and try?
Yes, sir. Actually, all the things which I will show you, they are just like basic data sets. And for larger data sets, it's not good, but yeah, intermediate level data set, it's fine. You can try with intermediate level. Just take your samples to be less, because it's not so effective right now. Everything is this is like a completely research topic actually. This is not at all I would not say that quantum machine learning is a university subject or anything. It is a research topic. It's not a subject actually. So that's why everything is currently uncertain, and you will not get
For smaller data sets, what is the maximum ceiling for that? So for larger sets,
maybe you can take 50 or 100 data points. That's it.
Okay.
Yeah.
Okay. So
not in thousands. Yeah.
From larger data sets, we can just sample out some 50 for different.
Yeah. Yes. Of course, you can do that. If you have a data set with 80,000 images, you can maybe sample out like 50 or 100 images.
Classify into similarities and take some few samples out of that, some 50 to 80.
Yeah, exactly. That can be done. Yes.
Okay,
all right.
Sir,
Another question. Yeah. Thank you so much, sir. Okay. QML based, I'm going to solve a SAT problem. Okay. I'm not very sure about this. Maybe you can use QML to solve a SAT problem, but for solving SAT problem, I think it's an optimization problem. So it's better if you use some annealing based method, maybe D-Wave systems are very nice for optimization purposes. So I think maybe you can use those kind of stuff, like, the adiabatic quantum computing. That is what D-Wave uses. Okay, Amirzuka, okay, sir, I will let you know about this. Okay, I am not currently sure right now, but yeah, as I mentioned you, maybe you can add noise to your simulator as well and simulate the circuit as well. That's also fine. That also works, because as I mentioned you in the last session when I was like speaking to Bob also, they are also doing some nice experiments of research, but even he also suggested me that you should like stick with the simulator for now rather than the hardware. So yeah. So maybe you can take Bob's advice. Bob was a professor at Oxford University. Okay, now he is at Cambridge Quantum Computing. He is a chief research scientist. So I just took his advice because they are so experienced. They are well known in the field, in the quantum computing field, and yeah, even they face problems with hardware. So it's not like that we face, but even bigger institutions also face. That's also like what I was a bit shocked to know. But yeah, that is also the case. All right. So maybe, yeah, thank you, sir. Thank you very much. And I will let you know about the emulators and everything. I'm not very sure, but yeah, I will let you know. I will let you know. I will like, maybe you can email me. Does everyone have my email, or should I type it again? Maybe I can just type it again. No, actually, I won't be writing any stuff, so I'm just keeping.
Sir, we have.
Have okay. A WhatsApp group. Sir, I am not familiar with any WhatsApp group actually.
Yes, I will
I
share.
can only be.
I will
Oh,
share
okay,
them.
sir.
Yes.
Okay, sir. Okay, thank you, sir. Then
Yes.
I am not sharing, sir. Okay.
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 Please, sir. Yes. I'll share it.
Okay. Then yeah. Then I will
And
just
sir,
show you the quick demo.
one more thing.
Yes, sir. Yes, ma'am. Yes, ma'am.
See, everything is on recording. So if this recording is with us, then we can see the notes also, whatever you are writing or you have explained. So how can we get these notes?
Ma'am, actually, I have sent notes to Darshan, sir,
Okay,
yesterday
yes,
for the
he
previous
also
session.
Yes, and notes are
on
shared
that.
actually.
Yes, yes, sir, you shared in the group. That I know. Okay.
Yeah, ma'am. So yeah, you will get all the notes. Not a problem with that.
Thank you.
Yeah.
Thank you so much.
Yeah. Thank you, ma'am. All right. So let me go to the demo. Okay. So let me show you. There's a small demo, like very small demo actually, just to show you that you can actually call, like, I mean, you can calculate quantum gradients. The syntax for PennyLane, you will find that it is very similar to IBM Qiskit. So I think that doesn't require so much of explanation. So I will just explain the basic stuff. So create a device means like device is actually the quantum simulator actually. This is your simulator. All right. So create a device means create a quantum simulator object. Okay, where for 5 qubits, where you can run your circuit, and then you create this quantum function. So variational circuit. So this is the quantum function which I mentioned you before in the theory. So this is the quantum function. And you can see this is very pretty straightforward. Like we are just applying Rx onto the qubit 0. Okay, qubit 0 means the first qubit, the second qubit, fourth qubit, fifth qubit, 5 qubits. And these are parameters means like theta1, theta2, theta3, like that. You can consider them like that. Different rotations. And similarly, you apply a broadcast. Broadcast means this one. So I have actually given you the documentation links if you want to know that C0 is broadcasted in a ring pattern. What is a ring pattern? This is the ring pattern, this pattern. So C0 is like this, So the first qubit control, second target, then again the second control, third target, then the third control, fourth target, like that, like that way, and then maybe the first control and the last target, and like that. So in a ring, it's like a rotating structure. So that is how you can, and you can utilize other patterns, and I urge you that you try with other patterns as well. These are various patterns available to create entanglements in the circuit. So here we use Rx, Ry, Rz, different gates, and we use a C naught to create entanglement. Then again, we use some single qubit gates like Rx, Ry, Rz. Then again, we do a broadcast, and we will be plotting this circuit, so and then we take a measurement. And now what we do is that we just narrow down the so we take this numpy function random, which will generate numbers up till like 10, just some random numbers like this, you can see. So 10 random numbers it will generate, and this becomes your parameter, and you just print them, and you can put it through the circuit. And this is the circuit. So you can see Rx, Ry, Rz, then Cx, which I told you. First control, second target, second control, third target, third control, fourth target, fourth control, fifth, and then in the end, last control, and this one target. Okay. So that is how it works. So yeah, cyclic, because it is cyclic. So then it will go here, and then it will come back again. Then again, the same thing. This one will be towards this side, this one, and this one will be towards the first one. So like that. Then we take a measurement. So in PennyLane, there are also options. Maybe I will share with you later. You can actually visualize your circuit in a nice IBM Qiskit fashion way as well. So they have actually shown that in the blog. Do you want to see in the blog? Should I show it?
Yes, sir.
Yes, sir, if possible.
Okay. It's nothing much. It's just
Okay.
like in the blog. Okay. Another question. Are we using different numpy? Yeah, actually, we are using this PennyLane dependent numpy. I forgot to say you. It's the same numpy, but it is PennyLane optimized. Like the people at Xanadu, they optimized that numpy for these calculations, so that they are more suitable with quantum circuits. So that's why it's not different. It's numpy only, but PennyLane based numpy, you can say. So I think that it is clear. All right. Yeah, thank you. So yeah, what I was going to show you, oh, not this one, sorry. Yeah. The blog. Okay, let me show it. So in the blog, they actually recently published a blog that you can actually visualize how to add custom gates, how to perform. Yeah, how to visualize quantum circuits in PennyLane. I was checking this out, and it is nice actually. You can print your circuits like this, like how we are doing. But if you if you don't like this style, maybe this may be more maybe a bit boring. You might like the matplotlib style, which is more lively. Then you can actually plot like this. Where is the circuit? Yeah, like that one. You can plot like this also. So I think they introduced this in the new version or something. I think I am using the old version of PennyLane. I haven't updated it. Like it's been many months. I haven't updated. So I will get an error if I do this. But yeah, I urge you all that you do this. Okay, try this. This is really nice. Is this clear?
Yes, sir.
You can give it a try. Yeah, you can give it a try. This is really nice. Maybe try plotting the circuit which I'm teaching you, maybe in this style. This is much more nice. It looks nice. Okay, then what we do, if you remember the parameter shift rule, we calculate the shifted. Okay, we calculate the shifted array, shifted list with np.pi/2. So this is how we do the shift plus. That means theta plus pi/2. This is theta plus pi/2. Let me write it so that you can compare it with the theory which we studied. That is what I always try to do. Compare, like trying to implement the theory with the practical, so that you can compare it easily. So this is theta plus pi/2, and this one is theta minus pi/2, which we saw in the class. Minus pi/2. Okay, and then yeah, then we just evaluated Q node. You already know, so I won't explain what is a Q node. Q node is just a wrapper. It just wraps your quantum simulator with the quantum function. That means this quantum function and the simulator, this dev. Once you apply this, then with your simulator in a one package kind of, you can say it's a single package. And maybe after you define the shift terms, then you can define the parameter shift rule, and in a loop you can apply it to all the parameters for the gradient. Say this is for one term, this is for single one, and this is for all the parameters. So we defined like 10 parameters. So we should actually get like 10 numbers. So you can see that there are gradients of 10 like with respect to each parameter actually. So these are 10 actually, 10 numbers with respect to these random ones which we defined here. Okay, so that's all. And this is just an example like to show you that PennyLane also has its built-in parameter shift rule. And if you compare the result, you will see that the manual implementation of parameter shift and the implementation which they have done, it's exactly the same. So it is just for verifying purpose. Just as I did with the Grover search, like we implemented it manually. And then I showed you that, yeah, you can take an encapsulated code, which is already provided by IBM, a function Grover, and then you use it and you get the same result. It's the same thing. I hope that this is clear.
Yes, sir.
Okay. All right. Okay. Thank you, sir. So
Yeah.
let me now show you variational quantum classifier. So variational quantum, I have provided explanations, and this is the same thing. So here you can see I have imported the optimizer, which I mentioned you in the theory. Nestro momentum. So maybe you can try with other optimizer as well. That I urge you to try different stuff. And these tutorials are of course adapted from the PennyLane tutorial, and you can go to the tutorial here in this link and find more information. So I've just adapted it and changed a few parts. So this code actually does your state preparation. This actually does your encoding, like you're taking your classical data and converting it into that Hilbert space. This is that code which is done. This is the simulator. So we take the angles and then we process those angles with the help of these parameters like ry. Then we apply some entangling layer like c0, then again ry, then some single qubit gates. It's a mix of things. And then we check this, that what this is the amplitude vector. So we actually do amplitude encoding. So in amplitude encoding, what happens is that if you have the states like maybe 0, 0, 0, 1, 1, 0, 1, 1, then the classical data will get encoded into the amplitudes. So maybe like this. So if you have this amplitude encoding, actually, it will work like this. Where is that? Yeah. Okay. Amplitude encoding, it works like this is an intuition how it works. So if you have if you created the states like 0, 0, then 0, 1, then 1, 0, then 1, 1. Okay. Then what you are going to do is that you are going to maybe some amplitude, maybe your classical data is like 0.53. Okay, then maybe it is like 0.29 somewhere, and maybe it is 0.44, 0.78, maybe like this. So this is like these are the amplitudes, and since these are associated with the quantum states, so that means you have actually encoded your classical x. Okay, so classical x was like this. So x was something like this, 0.53, then 0.28, then 0.44, and 0.78, and you just converted them classical X into the into amplitudes of quantum states. So that is all we are doing, nothing much we are doing. So it's the same concept. So just in code, that's it. And you can see the amplitude vector here. And also now, as you know, we have to define the layer, as I told you, H1, H2, you remember this one, H1, H2, the hidden layers, the PQC1, PQC2. So
Right.
yeah, so we just define the layer that consists of some rotations and a C naught, and this is square loss, which I already explained you. So this is like all thing I have already explained you. This is just like, having them in function. That's it. And this is the accuracy function, which will actually predict, like, how much accuracy, like, it will just mix, it will match actually, that whether the predicted is equal to true or not, like that kind of stuff, and how many of them are actually true, like how many predictions actually match with the true labels. So that is how you get the accuracy. And finally, we define this circuit. This is a variational circuit, of course, and we first apply the encoding. After applying the encoding, we apply the layers for each weights, theta ones. We take a measurement, and then we define this with the variational classifier. So in the variational classifier, we define the term weights and the bias, and they actually come from that params, the params which you will define actually. You can define it like randomly or anything. You can define your wish also. It's not that you have to use the random function. It's your wish. The optimizer will optimize it. And this is the cost. Square loss is the cost. Okay, so that's the one. And then we just take some data from the iris class. Okay, so iris is that flower data set which you all know. We just take it and we just print some samples, like this is the first original, then this is the padded. Okay, the padding is done just to match the layer which we have defined. Then we normalize them. So these are all classical pre-processing steps which you might already be familiar. All these things are done in classical machine learning. The same things you are doing in quantum. And so nothing is much different. And we just extract the features from the quantum circuit. All right. Now we can plot. We can give this a plot. So this is the original data. This is the padded and normalized data. And these are the feature vectors which we attain after the encoding. So since we have attained the feature vector, now we can split it. So the data set is split into training and validation. You will see that the steps are very similar to a classical machine learning. It's not much different. Only part which changed is that quantum circuit. That's it. Rest of the things, you will see that it is same as that of classical machine learning. So most of the part is actually classical and small part is quantum. But even that small part will actually play a huge role when we have a nice hardware to run these, and those hardware can actually deal with large data sets. Then you will see the real power that small part actually becomes a major role. And yeah, here is the training thing. So it is the same thing, like we define the batch size, we take the feature of training vectors in batches, and then we take the Y, which is the labels, and we apply this opt.step. You might be very familiar with this. We apply the optimizer, this optimizer to this one, to the parameters like var init. Var init is the initial parameters which you have provided, which we have defined above here. Okay, yeah, var init here, this one, yeah, random. We randomly chose, and then we apply the optimizer, then we make predictions, the same steps, and we calculate the accuracy, and we keep on printing that. So you can see that slowly the accuracy converges to like 1, validation accuracy. We will see training is nice, and the validation, we see that it is like sometimes converging to 100%, sometimes 92%, and like that. So it is able to predict the data well. And this is just a code for plotting, like I will just show you the plot. This code is just a matplotlib code, actually, nothing much. So there is nothing much to explain actually here. It's all like, you are just plotting these things which you collected your data, and you are plotting them like this. So this is like, class 1 train, class 1 validation, class 1 train, class 1 validation. So you have various data points and they have been, classified correctly. You can see the region. So there are a few points which have been misclassified. Like you can see these blue ones getting towards the red ones. Okay, but there is a margin, and you can see that, yeah, since they are they are towards the, like, you can say the left side maybe. So left side of margin means this is some flower class, right side of margin means another flower class, and we are able to see that we get some nice accurate predictions, and some blue points are actually on the margin, and some of them are like, misclassified points, like that. So that is the basic notion of a variational quantum classifier. And I think this all is working according to the circuit diagram which we already drew. So yeah, with that I would like to conclude. If I hope that this is clear.
Sir, very beautifully you have shown those, represented those results. Very
Yeah,
nicely.
thank you, ma'am. The nice visualizations, it helps you a lot to like appreciate the concepts. Whatever we write in theory, and then when we just see it
I
live.
think that is all as per MPL. MPL using
Which
MPL.
one?
This
Yeah,
color
this one is MPL.
yes.
Yes, this is Matplotlib. Of course, this is Matplotlib. You can also use other libraries like maybe Seaborn or something, but yeah, Matplotlib is easy.
Nice, nice. Nice.
Yeah, so most of the code is actually from classical machine learning. I would say that only quantum part is only the simulator and that rotation gates and all those, but most of it is like classical. So not much is quantum, unfortunately, but yeah, we are reaching there slowly. Soon it will be more and more quantum and less classical, like that. So all right. So yeah, thank you, ma'am. So
Okay,
I
so I
think,
think there are no more queries, right?
yeah, and I will share the materials with you, sir.
Yes,
Uh,
yes, fine,
yeah, by evening I will share.
fine. Okay, so we are at the end of this 13th session of our FDP. So I would like to thank our distinguished speakers, Miss Gopika Chaganti ma'am, IBM Quantum Developer, and Mr. Srinjoy Ganguly sir for making excellent presentations once again on variational circuits, quantum gradients, and variational quantum classifier with PennyLane. And making these sessions really very interesting and meaningful through hands-on sessions, practical aspects, I mean to say. So we are very much thankful to you, sir and ma'am, for sharing your precious knowledge with all of us. It's really intelligent and thankful. So thank you very much. Thank you all participants for your kind attentions and patience as usual. So thank you. We will start with our next session within next 15 minutes. So thank you all.